Hello and welcome to lecture 18, which is the first in the series of bonus lectures. That is, these lectures are going to be related to problem sets which are extra credit. So congratulations, you're done with the main material of this course. In this lecture, we're going to wrap up the forced top equations of motion. We're going to solve for its precession in the absence of notation, and also we're going to start the Hamiltonian approach. So let us first review what we were focusing on last time. And last time we were deriving the equations of motion for a forced top. So we have a top whose symmetry axis makes an angle theta with the vertical direction. This top feels the force of gravity, and its center of mass is displaced from the surface to which it's attached at a fixed point by height hcm. So we wrote down the Lagrangian, and we found that Lagrangian contains three cyclic variables: psi, phi, and time. Each of these corresponds to one conserved quantity per each cyclic variable, or three conserved quantities in total. These are the p psi, p phi, and pt, or energy. All of the three are conserved quantities. And we found that the energy conservation places constraints on the theta motion of the top. Namely, because of the energy conservation behaving similar to a radial motion of a particle in central effective potential, the motion of a forced top will be bound between the minimum and the maximum values of theta, theta 1 and theta 2, two turning points. And we showed that there are three types of two-dimensional motion that the tip of the top, or the axis of symmetry of the top, can trace out. Either we have continuous precession in the phi direction, or we have precession that periodically stalls, or we have precession that changes its sign. We were able to glean these trends from writing down the equations of motion that corresponded to the conservation of psi and phi conjugate momenta. So how have we been able to reduce this whole set of equations to quadrature? Well, we wrote down that the conservation of the psi momentum reduces to this form, where psi dot is expressed as a function of two conserved variables, the z and the 3 angular momentum, as well as the theta variable. Same thing about phi direction. Phi dot is expressed through a function of Lz, L3, and theta. And the energy conservation gives us the ability to directly integrate the theta equation and reduce it to quadrature. And because now we are able to reduce it to quadrature, namely, we can write that theta is equal to theta as a function of time, which is what the sequence allows us to arrive at. See, we get time as a function of theta, therefore we can invert that function and write theta as a function of time, then knowing this solution, we can plug it in back into both of these over here and over there, and therefore we will be able to express psi and phi as functions of time, because the only unknown theta here is now known because we have reduced it to quadrature. So the whole system is reduced to quadrature. And in the next part of our lecture, we're going to take a look at a specific case of no nutation. So we're going to consider the case of theta dot is equal to 0 or theta equal to a constant. I'm going to see you there. Please don't forget to do the quiz, and we're going to have more fun with the forced stop. Hi, and welcome to part 2 of lecture 18. Here, as advertised, we are going to look at pure precession. That is, there will be no nutation, there will be no changes in the theta angle. We're just going to be looking at how our force stop precesses in the phi direction. Let us write down equations of motion for theta, for nutation. So the momentum conjugate to theta is given by I1 times theta dot. And therefore, we can write down the equations of motion, which will be P theta dot is equal to I1 theta double dot, or according to Euler-Lagrange equations, that is also given by dl d theta, which we can compute from the expression for L. So all we've done, we've just taken the partial derivative of the Lagrangian with respect to theta. And we obtain this expression, except that here should be a square. Yeah, that's good. So now if we're interested in steady precession, that means that our value of theta is a constant, or theta dot is 0. And from here, it means that all of this is going to be 0, because if theta dot is 0, it means that theta double dot is also 0. Noticing that this is omega 3, we can rewrite all of this equation of motion in a simpler form. Notice that this is a quadratic equation for phi dot, the precession rate. So what we can now do is we can solve this quadratic equation. But let us first take a look at a few useful limits. So for instance, note that in the limit when there is no gravity, that is, we have a free precession of a spinning top, then we get phi dot, so we cover this one. One of the phi dots cancel out because phi dot equal to 0, a trivial solution is not something we're interested in, and we can write down that phi dot is equal to I3 omega 3 divided by I1 cos theta. This is the free precession frequency that we derived previously. So everything is consistent. Our equations of motion reduce in the limit of 0 gravity to the free precession equations that we considered earlier. Let us now consider the case when our gravity is not 0. And in this case, let us first focus on the case of a fast top, just like that simplified case that we derived at the very beginning of forced top part of our lectures. In this case, we're going to have two roots. If we're dealing with the fast top, that is, if omega 3 is much greater than phi, in this case we can neglect the term that's proportional to phi dot squared. This term will be negligible compared to the others. In this case, we can obtain that phi dot is equal to mgl divided by I3 omega 3, which is precisely the answer that we got for the precession of a fast top. And remember that fast was that the kinetic energy of the rotation of the top exceeded the potential energy of the top. The other root, so this was root 1, the other root, root 2, we can obtain by a little bit of a cheat. We know that by Witt's theorem, the product of two roots is giving us the ratio of mgl divided by I1 cosine theta, c over a. So from here, we can figure out what phi 2 dot will be, what the other root in the limit that is not omega 3 greater than phi dot. Hey, look at that! We have gotten the free precession frequency right from here. So as you can see, in the limit of a fast stop, we can neglect the phi dot square term and we can obtain the precession frequency of the fast stop. And at the same time, there is a second solution for the precession, which gives us the free precession when we can neglect gravity altogether. So this is just like in the absence of forcing. This wraps up the discussion of forced top, and I'm excited to announce that in the next part we're going to start the next exciting topic, which is Hamilton's approach. Feel free to do the quiz, and I'm going to see you in the next part, and we're going to have a lot of fun solving the Hamilton's equations. See you then. Hi, welcome to part 3 of our awesome lecture 18. Here we're starting the Hamiltonian formulation of equations of motion. So why do we need a new approach? We already have a Lagrangian approach, we're happy, we don't need anything else. Well, let's try and look at how the Lagrangian approach works. Well, in Lagrangian approach, we have this weird situation that the momentum and the coordinate variable, they're not symmetric. You see p is equal to dl dq dot and p dot is equal to dl dq. Wouldn't it be nice to switch to a set of variables where the equations of motion for each of these variables would be symmetric relative to each other? And Hamiltonian formulation treats variables more symmetrically. Namely, what it does, it switches from qq dot variables to qp variables. So in Lagrangian formulation, we're working with the q and q dot independent variables, coordinates and their velocities or time derivatives. And in the Hamiltonian formulation, we are working in the coordinates and momenta. And as you will see in a moment, when we work in these coordinates, the equations of motion for q and for p take very similar symmetric forms. So how do we go from Lagrangian to Hamiltonian formulation? For that, we use something that is known as Legendre transform. So let us illustrate Legendre transform on a thermodynamic example. Suppose we're giving heat dq to a thermodynamic system. That will result in its increase of entropy, TdS, or we can express it in terms of its increase of the internal energy plus the work that the system can do, du plus pdv. So if we express the differential of internal energy, we will see that it is a function of the variables S and V, because these are the differentials that are present when we difference U. So we can write down that the internal energy is a function of the entropy and the volume. Now we can make a change of variables. So for instance, we can rewrite this in the following way. So all we've done, we have added S dt and we subtracted off S dt. And otherwise, this thermodynamic relationship stayed exactly the same. However, now we can introduce a new variable, F, whose differential is given by du minus Ts. And that is called the free energy. And we can write it out as minus S dt minus P dV, or we can write it out, because we see now that F depends on the thermodynamic variables T and V only. We can write it out as F is equal to a function of T and V. So what just happened here? What we've done is we have switched variables from SV to TV, and we've accomplished that through a version of Legendre transform, which looks like this. We have switched from the thermodynamic function U, that was a function of S and V variables, to function F, to the free energy, which is a function of T and V variables. So we have traded entropy for temperature. And we've done that by subtracting Ts from the internal energy. Or because T was a partial derivative of U with respect to S, so this is T, we can write it out as, we can write F out as U minus du ds times S, and that is Legendre transform. We can do the same exact thing for Lagrangian. So you can see that the Hamiltonian, or the negative of the Hamiltonian, will be equal to the Lagrangian minus dl dq times q dot. And so what we're doing is we are trading the q dot for P. So similar to how we traded entropy for temperature, here we're trading q dot for P by subtracting off the partial derivative of L with respect to the variable that we would like to trade, times the variable itself. With this insight, in the next part, part 4 of our lecture, we're going to derive equations of motion in the Hamiltonian formulation. And I'm going to see you there. Bye! Hello and welcome to part 4 of lecture 18, where we are finally going to derive equations of motion in the Hamiltonian formulation. To do this, let us recall the definition of the Hamiltonian. Now, if we take the differential from both sides of this equation, then we're going to get dH is equal to dH d every variable times the differential of that variable, dH dq times dq, plus dH dP times dP, plus dH dt times dt. And on the other hand, we can do exactly the same thing. We can take the differential of the right-hand side of this equation, and we're going to get dP times q dot plus P times dq dot minus the same exact thing as what we did with the Hamiltonian, but with a minus sign, right? And with different variables. Instead of P, we're going to have q dot. So it will be dl dq times dq minus dl dq dot times dq dot and minus dl dt times dt. And now all we need to do is, because all these variables are independent, we need to collect the terms that are multiplying the same variables. After realizing that this term and that term, they actually cancel each other because P is equal to dl dq dot. And so now suddenly we actually can identify the terms. For instance, we have dq over here and we have dq over there. So the prefactors are going to be giving us that dh dq is equal to minus dl dq and equal to minus p dot from our Euler-Lagrange equations of motion. We can do the same thing for dp, and we will see that we have dp over here and we have dp over there. So what we're going to get is that dh dp is equal to q dot. And finally, we can do exactly the same thing, but with time. And we are getting that the partial derivative of Hamiltonian with respect to time is negative of the partial derivative of the Lagrangian with respect to time. So from these first two equations, we can get the Hamiltonian formulation for the equations of motion. And let me change the color here to make it bright. This is how the equations of motion look like. Q dot is equal to dh dp, and p dot is equal to minus dh dq. So as you can see, the Hamiltonian formulation treats Q and P symmetrically. The only difference between the equations of motion is the presence of the minus sign in the P dot equation. So what we've done here as a recap, we've started with the definition of Hamiltonian in terms of P, Q dot, and the Lagrangian. The definition that we obtained a long time ago, we took a differential of both sides of this equation and we collected the terms and assigned the prefactors to each other. Because all of these variables are independent, therefore this relation should hold true for any value of dp, dq, and dt. Therefore, the prefactors in front of dp, dq, and dt should vanish independently, and that is precisely why we can write each of these three equations. And as a recap, the Hamiltonian formulation of equations of motion is more symmetric in the sense that it treats the variables Q and P in a more symmetric way than the Lagrangian formulation does. So what happens in the case of when we have not just one degree of freedom, but many degrees of freedom? In this case, we're going to be able to readily generalize this to multiple variables. This was for 1 degree of freedom, and now we're going to write down for many degrees of freedom. As you can see, we can easily generalize the expression for the Hamiltonian by summing up over pi q I dot instead of just having pq dot. As you can see, we can generalize the expression for the Hamiltonian from 1 degree of freedom to multiple degrees of freedom by replacing pq dot with a sum over pi qi dot. And that's the only real difference in the expression for the Hamiltonian, but we already knew that from before. Finally, the equations of motion for qi and pi carry over from a single variable case. All we get is we add an index I on both sides of the equation. So the equation of motion for the ith coordinate becomes qi dot is equal to dh dpi, and the equation of motion for the ith momentum takes the form of pi dot is equal to minus dh dqi. So each variable keeps on to itself. Q dot I is dh dpi, and we repeat that for every degree of freedom, however many of them we have. So I goes from 1 all the way up to the number of degrees of freedom. So these equations are known as canonical equations. And consequently, Q and P are known as canonical variables. Now that we know how to write down the canonical equations, we can put them to action. And in the next part 5 of lecture 18, we're going to develop an action plan and apply it to a couple of examples. I'm going to see you there. Hello, awesome people, and welcome to the last part of lecture 18, part 5. Well, now that the board is clean, I'm going to re-announce the topic of this part of the lecture, and namely, we're going to present the algorithm that will allow us to apply the Hamiltonian approach to solving problems. So how do we use Hamiltonian formulation in practice? Well, that's our algorithm. So suppose that we are given a Lagrangian, which is a function of coordinates q, velocities q dot, and the time. Then we're going to compute the momenta as dl dq dot. Then we're going to invert the expressions for momenta to get the values of velocities expressed as a function of coordinates, momenta, and time. And now that we are able to eliminate q dot in favor of q, p, and t, the new coordinates, we are going to be able to compute h as a function of q, p, and t using this expression. And from then on, we can write down the canonical equations of motion. Q dot is equal to dh dp, and p dot is equal to minus dh dq. So let us take a look at a few examples. Consider a particle, a point particle in a potential. So let us compute its momentum, right? And now we invert this relationship to compute the velocity in terms of the momentum, just like we did here, velocity in terms of the momentum. The next step is to compute the Hamiltonian in terms of the coordinates and momenta. Plugging in x dot here, we're going to get that the Hamiltonian is p times p over m minus l, or p squared over 2m plus v of x. And as you can see, we have achieved our goal. We have expressed the Hamiltonian in terms of the coordinate x and momentum, and it doesn't depend on time. So bingo, the energy or the Hamiltonian itself will be conserved. We will be talking more about energy conservation later. And now we can write down the equations of motion. X dot is equal to dh dp, and that is equal to dh dp simply p over m, and p dot is equal to minus dh dq, or minus dh dx, which is simply minus dv dx, because momentum is an independent variable of coordinate, and so that's why this term doesn't contribute anything towards the derivative of h with respect to the coordinate. So that's example number 1, and before we to wrap it up, we can now unite these two equations together into the equation of motion that looks like that. So what we've done here, we've plugged in p into the second equation, and we're able to get it all sorted out in a single equation, where the acceleration is given by the gradient of the potential divided by the negative of the mass, or simply x double dot is equal to f over m, something that we knew, but this is nice to be able to get it from the Hamiltonian approach. Let us consider a little bit more involved example here. Consider a Lagrangian in this bilinear form. So Lagrangian is 1/2 of a matrix Tij multiplying Qi dot and Qj dot, multiplying the velocities, minus V, the potential that depends only on the coordinates, doesn't depend on time or the velocities. In this case, what are we going to do? We're going to compute the momentum associated with the ith coordinate, so ith conjugate momentum, which will be simply dl dqi dot, and that is going to be equal to, in order to invert this matrix expression, we can use a matrix form where we will be able to write down the matrix of velocities as the inverse of the T matrix multiplying the P vector. So the vector of velocities as the inverse of the T matrix multiplying the P vector. And we can compute the expression for the Hamiltonian as, so I guess let me make a brief stop over here. So the Hamiltonian, we can write it out using the definition of Hamiltonian, which is PQ dot minus L, of course the sum over the variables, if we have plenty of them, if we have multiple of them, degrees of freedom. So here we're achieving that using the vector notation, where we are converting Q dot vector into a row, so column vector into a row vector, and dotting it into the P vector. So this is equivalent to Pi times Qi dot. And we're subtracting from here expression for L, which is this, right? It will be 1/2, and then we have the matrix product like this, which represents this expression that's written out in components, plus V. So the minus sign becomes a plus because this is Pi times Qi dot minus the Lagrangian. So now what we can do is we can use this expression for Q dot and plug it into here. So everywhere where Q dot appears, we're going to be using this expression for it. And we're going to arrive at, so let's go over what we just obtained. So as you can see, when we plug in t to the minus 1 times p over here, we're going to get p tilde from tilting this whole expression. So we're going to flip the order and we're going to get p tilde times t to the minus 1 tilde, but t is a symmetric matrix, so it doesn't matter whether we tilde it or not. And then this p is retained from here. We're doing something very similar for the rest of this expression. So q tilde takes exactly the same form, p tilde times t to the minus 1. Then there is our t that we retain from the left-hand side over here, and we're multiplying it by q dot, which is simply t to the minus 1 times p. So this is where our expression for q dot lands. So now that we have gotten this expression straightened out, we can notice that a few things cancel out. For instance, this one, matrix cancels that matrix. So what you see here is that this term is twice that term. So what we are going to get is 1/2 of the same term as here, plus the potential energy. And that is the answer for the Hamiltonian in this problem. That's all for today. Thank you very much for your attention. I'm actually not sure whether I'm going to come up with a quiz for this one because this is an optional set of lectures. So I'm going to leave it up to you to enjoy them. But maybe I will come up with something. So have a wonderful rest of the day, and I'm going to see you in lecture 19. Bye.